Okay, so hello everyone, I'm Chenyuan, and today I'm going to talk about the coexistence of ultra-heavy and ultra-relativistic Dirac Quasiparticles in sandwiched graphene. And this work is done in collaboration with Professors Sachdev and Alex Khrushchev, and also in collaboration with Professor Kaksera's group in DFT calculations. So we know since the discovery of correlated insulators and superconductivities in twisted bilayer graphene, we know the effective two-dimensional heterostructures have been very successful candidates for the Moray-induced correlated phenomena. For example, we know there's many recent experimental progress in systems with more than 2 layers. For example, we have untwisted ABC trilayer graphene on top of a hexagonal boron nitride, and we also have the twisted double bilayer graphene. So we're looking for some new platform to study these correlated phenomena with a particular focus on the trilayer geometry. So here is what we study. We call it twisted sandwich graphene because naively we can see there are 3 layers of graphene. And also we keep the top and bottom layers untwisted and only twist the middle layer by small angle theta. So this way we can see the Moray brilliant zone is almost the same as the twisted bilayer graphene. And in this configuration, we see a high degree of symmetry is retained in the system. And also it also has a stronger effective interband coupling compared to the TBG model. So naively we would guess it would propose larger magic angles and also enhance correlated states compared to the TBG system. So here is our DFT tight binding calculation for twisted bilayer and twisted monolayer on bilayer and twisted sandwich systems. We can see the main features of this twisted sandwich graphene is it has 4 nearly flat bands, which is similar to the TBG model, and it also has a Dirac cone, which is reminiscent of the single layer graphene. And we say the first feature, the flatness of first feature, is highly depends on the twist angle, the lattice relaxation effect, and also the external perturbation. So in our calculation, we find the magic angle at 1.61 degree. You can see it's larger than the TBG model. And we also note that this twisted sandwich graphene has an advantage over the twisted monolayer and bilayer graphene because you can see here the flat band features are largely obscured by the non-symmetric band hybridization. But here we still have the flat band that is similar to the bilayer case. And we see this actually to perfectly mimic the bilayer feature, we need to align the external layers of the bilayers to be exactly AA aligned. And so now we'll say that this experimental challenge actually is overcome by considering the lattice relaxation effect. So first, let's consider when there's no layer misalignment between the bright layers and see the lattice relaxation patterns for these layers. We can see here the white arrows denotes the atomic displacement, and this color shows how the local twist angle changed due to the relaxation effect. And we can see here, this is the Moray supercell as shown here. And this relaxation field can form some kind of spirals around AA sides, like here, and also around AB sides, like here. In fact, these spirals actually enhances the local twist angle in AA side and reduces the local twist angle at AB side. In this overall effect can reduce the total energy. That's the effect of this lattice relaxation. And it also has a slight change of the electronic structure. We can see that the flat band occurs at approximately 0.1 degrees smaller than the unrelaxed model. So now based on this analysis, we can see to investigate the effect of this graphene layer misalignment. So now we suppose we shift the top layer with respect to the bottom layer for a certain displacement D13 and keep it fixed. And then we can calculate the total energy as a function of this stacking between bright layers. Now we see in the A side there's an energy barrier. So here is the equilibrium state. We can see it's protected by about 20 millivolt per nanometer squared. And this is experimentally vital because it actually makes the A stacking of bright layers robust against these interlayer shifts. That means this bright layers will naturally relax to our desired configuration. And to understand this experimentally feasible model, the most simple way to consider is the effective continuum model. So here we can directly write the effective Hamiltonian for this tri-layer case, which is which is direct generalization of the McDonald's paper. So here we see these diagonal terms. These terms are just the monolayer Dirac Hamiltonian, which is rotated by theta over 2 for the middle layer and minus theta over 2 for the bright layers. And also this TR is the interlayer coupling, which is taken up to the first shell in the momentum space, like here. Actually, there are only 3 factors that has effect in this system. This is the interlayer coupling between AA sides, between AB sides, and the twist angle theta, which appears in T and also in this monolayer Hamiltonians. And now to further simplify this model, we can consider a chiral-symmetric limit, which only consider will put the interlayer coupling between A side to be 0 and only keeps the interlayer coupling between AB sides. So now in this way, we can find the effective continuous model. So here is what we get from the chiral-symmetric limit. We can see there's a perfectly flat band with a piercing through with a Dirac cone, and at this 1.55 magic angle. And if we put the angle slightly below or above this magic angle, we can see the lowest band is a dispersive band. And also we can see this character actually can be determined by this dimensionless twist parameter we define as alpha theta. Alpha theta is a ratio of interlayer coupling between AB side and the length of these wave vectors. And we can also calculate the Fermi velocity of this lattice band in terms of alpha. So we can see that this Fermi velocity will reduce to 0 at the first magic angle and then reappears, and then reduce to 0 and reappears, which shares a similar feature with the twisted bilayer graphene. And in this way, we can also find some higher order magic angles, which is called as alpha 2 at 1.57 and alpha 3 at 2.65 here. Here we plot this Fermi velocity in dashed line because here this angle is very small. You can see it's less than 0.5 degrees, so it's largely affected by the lattice relaxation model. So we probably cannot observe these higher order magic angles in the experiment. And we see this model is interesting because we can also do it by the leading order perturbation theory, and this gives the dependence of Fermi velocity in terms of this alpha theta. And if we solve for the flat band condition, we put the Fermi velocity to be 0, we can find the solution at alpha star equals to 1 over square root of 6. And actually, this provides an exact map to the twisted bilayer graphene by the factor of square root of 2, if you compare the Fermi velocity for TBG model by McDonald's paper. Okay, the last thing I want to talk about is the tunability under external electric fields. We can say if we apply an external electric field to the system, then the Dirac cone will split into 2 Dirac cones, one above and one below the flat band. And also the flat band will have a parabolic touching as the key point. So that means this electric hybridization between the flat band and Dirac cones can be directly tuned by this external field. And if we recall our previous research on this critical temperature in terms of this interband coupling, you can see this critical temperature will increase as we strengthen the interlayer coupling. So that means it's possible for us to observe a higher critical temperature for these twisted sandwich graphene systems. Okay, so to summarize up today, I will talk about this sandwich graphene can host some flat band piercing through the Dirac cones, which is protected by the lattice relaxation displacement. And its external fields can directly control between the electronic hybridization between the Dirac cone vertex and the flat bands, making it possible to observe a high temperature superconductivity in the sandwiched graphene. Therefore, we propose a novel and especially experimentally feasible platform for a broad range of exotic electric phenomena. That's all for my talks, and I'm open to your questions. Thank you.
Okay.
Okay.